And I'll start the recording also. That's going on. Okay, so we are there live, and now I'll start the recording also. Okay. So can you tell me now on YouTube, where is this? Naman, where in settings?
Yes, ma'am.
We are there live, and now I'll start the recording also. Let me stop this for a minute. Yes. So tell me, now, can you just tell me again? I'm in settings now on YouTube.
Ma'am, there is a section known as live chat. Go there.
Live chat on the. So can you tell me now on YouTube, where is this? Naman, where in settings?
Ma'am, can you please share the screen?
I think that is better. So tell me, can you just tell me again? I'm in settings now on YouTube.
Ma'am, there is a section known as live chat. Go there.
Just give me 1 second. So I will start on the. I'm sharing my screen, right? So can you tell me now? There's such a lag between. Is this in settings?
Ma'am, can you please share the screen?
So tell me.
Yes, ma'am. So on there, you will see the 9 dots. Click there and go to YouTube Studio.
Can you see my screen, Naman? Can you see my screen?
Yes, your screen is visible.
So I should go where?
Yes. Here, ma'am, go to YouTube Studio.
YouTube Studio कहाँ है, boss?
Yes, ma'am. So on there, you will see the 9 dots. Click there and go to YouTube Studio.
YouTube start. I have YouTube TV, music, kids, a creator for artists.
Or ma'am, click your profile picture. There, I think you will find YouTube Studio.
Okay, let's
Yes, your screen is visible.
So I should go there.
Yes. Here, ma'am, click on your profile picture, ma'am. Here on the top right corner.
YouTube Studio कहाँ है, boss? Okay, here I found.
So
Yes.
on there, you see the 9 dots. Click there and go to YouTube Studio.
Start. Okay, finally. Okay, now where is it?
Yes, ma'am. Go to content or live streams.
Yes,
There, I think you will find it.
visibility.
Yes, ma'am. There from uploads, click to live. There are 2 options.
Yeah, live stream, visibility, ऐसे है ना?
No, ma'am, not from here. We are streaming from the this thing, na? Like LifeLab India account. I think we should
Yes.
see that.
Okay, listen. I think we will take the. Yeah, that's true. LifeLab account. I don't know if Rajiv is there. Then he would know how to do that. Can you then just take it over with him?
Okay, ma'am.
Okay, because you are right, I'm in the wrong account to do that. But I think,
No, ma'am, not from here. We are streaming from the this thing, na? Like LifeLab India account. I think we should see that.
okay, listen, I think we will take the, yeah, that's true. LifeLab account. I don't know if Rajiv is there, then he would know how to do that. Can you just take it over with him? Okay, because you are right, I'm in the wrong. But I think, okay. Wait. Now, okay, listen, I think we will take the, yeah, that's true. Let's have account. I don't know if Rajiv is there, then he would know. Just take it over with me. Okay, because I am, you are right. Okay, guys. I think, okay. Wait. Okay, listen, I think okay, all right. Good afternoon, everyone. Good evening. Can you hear me?
There is a noise.
Can you hear me?
Some kind of echo is taking place in the background.
Ma'am,
Trying-
on your computer or Pallab sir's computer, close the live stream on YouTube. The voice is echoing there because of that. Or just press M on the YouTube tab. That will
You're right. You're right. So now it should be okay. Is it all right?
Yes, now fine.
Yes, sir.
Very good. So I think I will fix this chat in a moment. Let's get started first because people are here, people are waiting, and I think we should not lose any more time on that. Is that okay?
Yes, sir.
Very good. So welcome to the session number 12 for LifeLab Foundation QuarkNet India sessions on science, on astronomy, on particle physics. We are looking at the universe from different angles. You know, in particle physics, you go to the most fundamental building blocks, while in astronomy, you look at the sky and further, much, much further, in such a way that we will be able to connect the dots in between from the very tiniest particles where we look at CERN, for example. The orders of magnitude that we are covering are more than 30 or 32. So it's incredible that today we have with us an eminent outreach communicator who is well known in the field of astronomy in India and also abroad. Gourav Banerjee is currently pursuing his PhD in stellar astrophysics at the Christ, deemed to be University in Bangalore. He also has an MPhil in astrophysics from the same university and an MTech in astronomy and space engineering from Manipal University in Karnataka. He's been, as I mentioned earlier, involved in many, many outreach events and astronomy outreach for over 20 years. And I think that we have very exciting times ahead because there are many, many projects in astronomy in our country. I'm sure many of you have heard about them. We have the LIGO Mega Science Project of gravitational waves. We have the TMT, the 30-meter telescope, never built before, and India is a big partner, not only a partner, but a leading partner in this mega project. We are so happy to hear from Gourav about this work, and on all these many projects, he has been delivering more than 400 popular talks across the country. He is also founder member of the Kolkata Institute of Fundamental Science and Astronomy, an institute that is involved in popularization of astronomy and basic sciences. This is extremely important for our country because whatever we do in science has a direct relationship to the impact in society, to the sustained development goals of the United Nations. And you all, teachers, and many of you students are going to be the ones who are going to solve the global issues, the grand global issues that face life today. And of course, it's because of the involvement in basic sciences that this can happen. So we invite Mr. Banerjee, who is also an author of the book called Becoming an Astronomer. This is the first book published in India, which provides the details of how an Indian student can pursue astronomy as a career. So please join me in welcoming Gourav Banerjee, and we are very happy to have you here, Gourav. So we really we are all waiting to hear from you and to understand how we can encourage also bringing students to not only astronomy, but to science, but to STEM, engineering, and eventually make a difference. Thank you. Thank you, Gaurav, for accepting our invitation and being a part of this Team Life Lab Foundation for Education and Research. And I'm sure that this talk is going to make a big difference. Thank you. Please, over to you, Gaurav.
Well, thank you, everyone. Namaste to all of you. And it's a nice evening today at present in India, and I guess it is afternoon at Geneva. So welcome, everybody. I would first like to provide my special thanks. It is my delight, it is my pleasure to be a part of Life Lab Foundation and also coordinate India from almost from its inception time. I would like to especially thank Archana Madam, Pallab, my friend Pallab Rai Gupta, Arindam, Rajiv Gupta, whoever is involved in this good sessions, organizing such sessions on astronomy, particle physics. And it is the 12th session. So it's really a good initiative from your part, Madam, and every one of you. So there is nothing extra which I can say now. Today is the time where we can jump into astronomy. It is my pleasure to be the member or receive this opportunity to deliver the first talk of this so-called this designated astronomy month by Life Lab organization. So it is also, we should think of like that, okay, when we are delivering some kind of this first lecture type of sort of thing, we should be aware about the fact that only telling about astronomy might not help in every aspect. Let us try to delve deeper into physics and astronomy, and let us try to see how each and every branch of physics mixes together to help each other branch. So today, as a result of this great initiative from Life Lab, Archana Madam, well, obviously Pallab, my special thanks to you also. I know Pallab as my friend. He is one of the founder members of QuarkNet, and he is actually coordinating this astronomy month and all other sessions till now on behalf of Life Lab. A wonderful welcome and thanks to all of you. And let me now share the screen apart from going to talks. First, let me share the screen. So today, especially, I would like to discuss about one particular topic, which is on what is known as revealing stellar energy source. So what is this stellar energy source? Let me first tell a very basic about this. We all know that stars are generating energy at their cores. How that we know due to something known as nuclear fusion. Now this nuclear fusion process basically happens in the core of the stars. But how do we know about that? Can we go to the core of the stars to see whether this is happening or not? We cannot go to the core of the stars. Astronomy is a subject which can be considered as an abstract subject. So basically what we can do is we have to take the help of other branches of physics, basically physics, chemistry, mathematics, all branches come together to help us out. And basically we get this idea how we get everything about astronomy and other physics by studying the simple equations, by studying the simple laws of nature. Today, let me take all of you to a journey, wonderful journey or wonderful detective story, I will rather say, that how people first understood, how scientists first revealed that what I told just now, that nuclear fusion is happening inside the core of the stars. How people understood that. In science, or basically in humanity, there is a saying, what I feel is everybody knows that seeing is believing. Means if I can observe something, if I can see something, then only I will believe that that is happening. But every time that is not possible. We have to resort to experimentations, very hardcore experimentations or something else. Astronomy, in the field of astronomy, where there is basically no earthly laboratory. Astronomy is a subject where we study objects outside our Earth, celestial objects. And this is one of the great challenge for astronomers, for anyone pursuing astronomy. Why? Because for studying astronomy, if you study astronomy, you will not have a particular laboratory where you can bring the object you are studying in that lab. You cannot bring a star or a planet or sun or moon or the galaxies in your lab, cut it, test it inside, whatever is happening, the way which is actually followed in case of other branches of science, suppose in chemistry, semiconductor physics, particle physics. We can do experiments sitting in our art up to our best technological levels. And we can ultimately get the results, we can analyze the results and tell that something is happening. Okay, whatever we are getting, what is the inference of the result? But in case of astronomy, you cannot do that. You cannot bring the objects you are studying in any lab and ultimately do any kind of test. So what has to be done? To recover from this challenge, human intellect has helped astronomers and scientists. Let us today start a journey, or let me today tell a story to every one of you that how all branches of physics, almost chemistry, mathematics, all came together to solve one of the greatest puzzles in the history of humanity. How we understood that inside the core of sun and stars, actually nuclear fusion is happening. Because you cannot see the nuclear fusion happening, you cannot bring the star at itself. Also, whatever we study using our instruments and our technologies for a star, we cannot see the interior of a star. No way we cannot see the interior of a star. Then how we can say today with extreme, almost 99.9% confidence that nuclear fusion actually happens inside sun and all other stars. And the rate of nuclear fusion, the evolution of stars, these are all very well understood phenomena. We understand stars much better than we understand the life history of our own existence, the life history of humanity. We understand the life history of humanity less, but we understand the life history, the life cycle of stars much better than that. But how? And that how will be solved by some of the greatest detective stories which can, so today our detective story will lead to us to one of the finest investigation which humanity has ever carried out. I can bet at the end of this talk, everyone will agree with one of my sentence which I will tell now. This detective story of revealing stellar energy source can beat any detective story, even the finest Sherlock Holmes stories ever written in the history of humanity. So let us start this journey from very beginning. It is true that at the very beginning, from the ancient period of time, people are looking towards the night sky and they are wondering with awe and wonder. Why? Because night sky is beautiful. And natural curiosity of man obviously drives people to look above. So basically, looking towards the night sky is not something, it's not a habit. It's a natural curiosity for which people are looking towards the night sky. But while in ancient period, people used to look towards this type of night sky, they used to see so many things, so many objects, they didn't know what they are. As time progressed, the same night sky with the help of sophisticated instruments like telescopes, detectors, cameras, and other sophisticated instrumentation has changed their shape, changed their vividity. And now when we look at the night sky with the help of some of the finest instruments, we see the night sky is full of wonders, full of colors, full of stars. Basically, each dot you see in this picture represents actually is a star. So it's something amazing. Obviously, no one can see the night sky of this flavor from anywhere in the world with naked eye. This is taken from some of the most sophisticated instruments of the world. And to take such extreme, good, beautiful images, we have to take the help of something known as astronomical observatories. But before going to that, let me come to, from those ancient period, let me directly come to this portion. It was during the time of 19th century, basically 18th century and 19th century. So there were philosophers who used to see or who used to judge what kind of knowledge humanity has gained. So one of the French philosopher in 1835, he once wrote that it was in the nature of things that one can never or one could never know what the stars are. And it was correct up to the knowledge of that time, it was correct. What I have told before, if you think about that once more, that obviously, how can you know what stars are made up of? How can you know what stars are actually are, how they progress, whether they live or die, whether they are eternal, whether they have any life cycle or not, how far are they, what are their properties? How can we know what are the stars, what stars are, and what is their nature? Because there is no tool for us during 1835. But remarkably, the same time when the philosophers were writing this particular statement, they were unaware of the fact that the tool for invading the stars was accidentally already discovered. And that tool, basically, one of the greatest tool through which we can actually study the properties and evolution of stars is spectroscopy. But with spectroscopy also, whatever we study is the outer layers of the star. Basically, with the help of this spectroscopy tool, we can study sun, we can study star, but the radiation which is coming out from that star to us, which we can detect with the help of spectroscopes, that radiation is originating from the outer layer, the outermost, the surface of the star, which is known as photosphere of the star. So the sun which we look at, with whenever we try to see sun with our naked eye, please don't do that. But if you see the sun with the help of a filter or telescope, with the use of proper filter, or with our naked eye, the part of sun which we see actually that is known as the photosphere of sun, or surface of sun, or surface of a star. So it is from that region the radiation is coming to us, and when we study that, we can understand about the surface area, the surface layer of the star. But how can we study the interior of a star? That is not possible. As time progressed, around another 100 years later, one of the greatest astronomers, one of the greatest stalwarts, I can say, in the field of stellar astrophysics was Sir Arthur Eddington of England. So he wrote in one of his book that what appliance can pierce through the outer layers of a star and test the conditions within? Because he was well aware, he understood that whether it is okay, we can gradually study the surface of a star. We can understand the properties, what is going on in the surface of the star. But is there any tool by which we can go inside the star? There is no such tool which exists to us, at least till that time. Is there any tool which can ultimately pierce through the star, and we can actually invade the interior of the star, and we can actually see what is actually happening in the interior of a star? There was no such tool, no such appliance. And that was the dilemma, that was the paradox. This is the question which was put over by Arthur Eddington in 1924. Now let us see after that what happened. So this was the condition of astrophysics during the first half, or during the first quarter of 20th century. Astrophysics was such a abstract subject till that time that basically proper physicists were not, during that time, Lord Rutherford, Enrico Fermi, all great stalwarts of physics, the proper physicists were not at all bothered about problems of astrophysics, because they knew that astrophysics deals with some abstract science, abstract knowledge, and there is a huge amount of error. Whatever we are calculating in astrophysics during that time, huge amount of error was there. So great physicists or physics researchers and physics people basically were not at all bothered about astrophysics during the first quarter of 20th century. They were much bothered about a very good thing was happening during those days. Huge progress was going on in particle physics, nuclear physics, atomic physics. The Bohr's atomic model came into effect. Quantum physics was there. It was just born. So huge progress was going on those areas. And naturally, young brains were driven to those areas rather than in astrophysics, because astrophysics did not have a solid footing during those days. So this was what we were having after 2000 years of our studying the sky in 1920s. Now, as time progressed, gradually different sophisticated astronomical observatories actually developed. And as these were developed, we started understanding about astrophysics. There are various such astronomical observatories with large telescopes inside each observatory dome like this. These observatories are present almost in every remotest corner of every good countries, and they are also present with us. So this is like the photo of one of the greatest telescope which we have in our own country. It is situated in a place called Kavalur, which is in Tamil Nadu. So you can actually have a look into this dome. It's a huge telescope, and how huge it is, just you can have a look into this lady. Just a comparative view will give you an idea how huge this telescope is. So like this, not only in our own country, not only in other countries, we have nowadays proper, very good telescopes, sophisticated instruments in space also, like we all know about Hubble Space Telescope. So basically, these are the instruments which have given us the idea or proper understanding of astrophysics gradually. And one such story which we have revealed through understanding of astrophysics is this. We have very well understood, though there are gaps to be filled, there are precise gaps to be filled, but we have very well understood how a star is born, how it progresses in its life, and how it ends its life. I will not go to the details of a stellar life cycle today, but one important fact from this stellar life cycle I will bring into our discussion today. That is, for a star to be born, and after a star is born, a star to remain proper and stable, there should be some energy which is generating inside the star. Energy generation must take place inside the star. Otherwise, the star will not remain stable. And how that energy is generated? Well, it was in 1938 when German physicists, basically not astronomers, they were all nuclear physicists. As I have told earlier, nuclear physics, atomic physics, they were in the hot seats during those days. So C.F. von Weizsäcker, he was the physicist who first discovered one particular reaction cycle, which is known nowadays as carbon, nitrogen, oxygen, or in short, Cno cycle. And he identified that most probably this is one chain reaction cycle which is responsible for the energy generation inside stars. But within a year, another master nuclear astrophysicist or nuclear physicist, I will rather say, Hans Bethe, he was also a German. Within a year, he actually understood the importance of people to ultimately go into astrophysics area. Hans Bethe was one of the masterpieces in the field of nuclear physics. And he understood that now time is gradually approaching during 1938, 1939, that when people should actually take care of astrophysics, people should also do astrophysics research. There are so many present problems which can be solved in astrophysics, and that can actually help in modern fundamental physics also. So it was he who actually, what the story goes like this, he actually organized one small conference in Washington, D.C. in America in 1939. And it was he who persuaded some of the topmost physicists to join that conference. So Enrico Fermi, Niels Bohr, they all, Wolfgang Pauli, these are all heavyweights in physics. They all joined that conference. And that conference was actually given impressive views directly by Einstein also. He was one of the person who told that, who actually gave a letter that yes, this kind of conference is necessary. So Hans Bethe in that conference gave a talk, and where he actually put forward that now time has come, we should understand very well how stars energy is generated inside their core. How energy generation is occurring inside stars. We should know this. Without knowing this, we cannot progress further in a very detailed way, even in any part of fundamental physics, not in nuclear physics, not in atomic physics, not in particle physics also. And after this conference was over, gradually the greatest physicists, they started understanding that it is now important. Well, it is also important to do research in other areas of physics, but astrophysics is very, very important. After this conference, within few months, Hans Bethe, being the master of nuclear physics, he chalked out in very details that what kind of reactions are actually going on inside stars, which ultimately generates energy. And he published his results in one of the stalwart papers, which is known as Energy Generation in Stars in 1939. One can read that paper. It's a fully detailed paper where he gave the complete details, the rate of energy generation, what kind of energy generation mechanism is happening, which reactions are happening in which kind of stars, everything he had mentioned with great details. So now the question is basically what kind of reactions are going on inside stars. What Bethe told, or what Bethe have postulated or hypothesized, was this. In case of massive stars, massive means basically those stars which are more massive than Sun, at least around more than 2.5 times the mass of Sun, or more massive than that. Those kind of stars generate mainly their energy with the help of a cycle of reaction known as Cno cycle, which was discovered by Weizsäcker 1 year earlier. I will not go to the details of these reactions. Basically, what happens in this cycle is carbon nucleus takes part as the form of a catalyst, and it actually reacts, or it actually fuses with proton to form nitrogen, one isotope of nitrogen. That nitrogen ultimately decays to carbon, and gradually that process continues. Again, carbon, the heavier isotope of carbon actually captures another proton. It becomes proper nitrogen nucleus. The next step is nitrogen again captures another proton. It becomes a lighter isotope of oxygen. And finally, that oxygen decays to nitrogen again. That 15 nitrogen, that isotope, the heavier isotope of nitrogen, ultimately captures another fourth proton, that is one hydrogen nuclei, to make one helium nuclei. Basically, this whole fusion process takes place in the presence of some carbon, which acts as a catalyst. At the end of the reaction, that same carbon is again returned back, but in the end product, this process actually fuses some of the protons. 4 protons are fused together to helium. And at the process of doing this, you see energy is liberated. This is the energy which is actually transported. A part of this energy is transported to the surface of the star. And this is the energy generation which is happening in case of a massive star. So basically, the massive stars having mass more than 2.5 or 3 times the solar mass, or more than that, the energy generation is happening with the help of this particular chain reaction system, which is known as Cno cycle, where 4 protons in the presence of carbon is basically fusing to give helium and ultimately energy. But in case of less massive stars, what happens if a star is a sun-like star, if a star is having a mass less than 2.5 solar mass? In those stars also carbon nitrogen cycle happens, but the percentage of Cno cycle generating energy in case of low massive stars is less than 1%. 99% of the energy in low mass stars are generated by another process, another chain reaction system, which is known as proton-proton chain reaction. Why? Because you see it's a 3-stage process. In the first stage, you see 2 protons. Basically, proton means a hydrogen nuclei. 2 protons are taking place to fuse into heavy hydrogen, and ultimately that heavy hydrogen is actually taking or combining with another proton in the second stage, that is forming a lighter isotope of helium. And in the similar way, in the third step, another helium isotope has been formed. So 2 helium isotopes combine together to ultimately generate or fuse to a helium nuclei, and ultimately 2 protons come back. And in the whole process, energy is generated. So basically, following Einstein's that famous equation, E equal to mc square, energy equal to mass into light speed to the power square, following this relation, energy is generated when protons actually combine or fuse together to give helium as a byproduct. This happens basically in both the processes, Cno cycle and also in proton-proton chain reaction. Now, these reactions are extremely important. Gradually, we will come to these portions. Basically, the way I have told is very easy. It is not so easy in case of a star. Why? If you look carefully, anyone who has read basics about particle physics, naturally, now is the time when, kind of some disbelief will come to your mind that, okay, whatever you are telling now, till now, it's okay. I am assuming that that is correct. But now what you are telling, something is greatly wrong. Why? It should be wrong. Okay, let me show another picture. That same proton-proton reaction, here it is picturized. The same thing. See, energy is being produced, protons are fusing, and protons are fusing to give birth to a helium nuclei, and at the end product, energy is produced. But something is extremely wrong here. And there begins the twist. The twist started from that time onwards. What is wrong in that case? Anyone who has a very basic understanding of physics, you have read in even class 8, 9, 10, you can actually point out that, see, protons are basically positively charged. And we have read in our school that positive charge, two positive charges repel. They cannot come together and fuse. They cannot come close together enough to fuse. Then how can two protons are coming together and fusing? You are telling that this particular reaction is happening inside stars. This first reaction should not take place. Both the protons being positively charged, how they are coming towards each other and very close to each other, and ultimately they are touching each other and fusing to a heavier hydrogen. This first reaction, something is extremely wrong here. How can this happen? Basically, without going to details, I will just give the answer today. This can happen. If in the realm of classical physics you remain, this can never happen. But this problem was solved, this fantastic puzzle was solved in 1928 by another great Russian physicist known as George Gamow. Whoever has read some of his books like 1, 2, 3 to Infinity. So it's a fantastic book, you can have a look into it. So he was also a great teacher, great communicator, science communicator. He was the person who first identified that we have to take help of quantum physics to answer this question. Yes, positively charged two protons can come very close together, so close that it will ultimately fuse. And the process by which this happens is basically known as quantum tunneling effect. It is a magic in nature. This is absolutely happening in nature. It's a magic. I will not go to the details of what quantum tunneling effect is, just to give you an understanding why I'm telling this. This is a magic. Basically, what quantum physics tells us is this, one word, one sentence, that every particle can behave like a wave and also like a particle. Same way. Opposite also is true. Every particle can behave like a wave also. So basically what happens is, suppose you take two protons, one here and one here, left hand side of the hill, right hand side of the hill. These two protons can never fuse because they are having positive charge. As they come closer together, as they approach closer and closer, there will be an unseen barrier which will be created, a barrier like a hill, a barrier like a volcano, or a barrier like a wall will be created. And that is, in physics, it is known as Coulomb Barrier. No need to go to the details of that. Just like a picture, you can think like that, as they are trying to come very close to each other, nature will not allow them to fuse because they both are positively charged, and some particular Coulomb barrier, some barrier will be ultimately created in between them. That barrier, the height of that barrier is much, much more than the energy possessed by these two protons. So the two protons can never hope to climb that barrier and ultimately climb and cross and ultimately come so close together so that they will meet each other and fuse. Crossing this Coulomb barrier or this hill-like barrier is impossible in case of classical physics. But what Gamow told was this. See, as quantum physics is telling us that sometimes particles, in certain cases, in certain moment, particles can behave like a wave also. If suddenly a particle, if this proton, which is a particle, behaves like a wave, then what can happen is a magic. suddenly it can pass through this barrier as if creating an unseen tunnel. And that is what is known as quantum tunneling. Without going to any other details, I will just say that this is how, just by creating a tunnel when the protons are acting like waves, during that time they can create tunnels, and they can, passing through these tunnels, they can actually cross that huge barrier, extensively huge barrier also, which otherwise in general case in classical physics it is impossible. So he solved this great puzzle that, okay, it is actually happening. With the help of classical physics, we will not be able to explain how two protons come together and fuse. But if we take the source, take the help of quantum physics, then we will be able to say, he proved with the help of numerical calculations that quantum tunneling is the way by which two protons can pass through a tunnel, unseen tunnel, and they can cross the barrier and they can fuse together. But so these are some of the features of quantum tunneling. Without going to that, what I am trying to say is this, the bottom line is this. Let's see what is the temperature of sun inside its interior. In the interior core of sun, the temperature is more than 10 million degrees Celsius. It's around 1.5 crore degrees Celsius, basically. And energy of particles, any proton or any particle is around 1000 electron volt. If you compare that, what is the height or what is the energy of this unseen barrier, it will be 1 mega electron volt. That means the energy of that particular, or the height of that Coulomb barrier, is 1000 times more than any proton's maximum energy. So in normal case, a proton can never hope of climbing that hill and fuse. Now the question is, okay, we understand, we are taking it as if it is true that through quantum tunneling this can happen. I am accepting. But can normal protons inside stellar interior having this much of temperature, can protons actually have, some of the protons actually have such huge amount of energy? That is also very, very, very impossible. The only way we can think of that they are fusing together is by taking the help of quantum tunneling effect. However impossible it seems to you, it is actually happening. Why it is so I can go to an analogy. Okay, if suppose this particular quantum tunneling is not happening, then we will not see any stars in the sky. Stars wouldn't be shining. So this is one way of telling, okay, an indirect way of telling that whatever you don't see, you will have to accept that, because you see things which can occur if that phenomena is not occurring. But, well, I accept this, you all can accept this with some dilemma in your mind. Well, I accept it, okay, if this is not happening, stars will not be there. But is there actually any way by which we can see the stellar interior? Is there actually any way we can see that nuclear fusion is actually happening? There was no, I have already told, there was no tool to see that. So there was no way. Scientists have to take this as if it is the law of nature. Nature has told the stars will not be there if quantum tunneling is not happening. And Gamow also told this. Whatever I am telling is correct. If it is not correct, we will not be there. Stars will not be there. We will also be not there. So it is happening. But the problem is not sorted out here also. That same equation, anyone having a better deep understanding about particle physics will have again problem. Okay, one problem, one very basic problem you have solved. And we accept that quantum tunneling is happening, two protons being positively charged are fusing. But still, everything is solved. Still, there are problems. See, I have told that in any case, carbon-nitrogen oxygen cycle or proton-proton chain reaction, in any case, energy generation is happening by fusing 4 protons to 1 helium nucleus. But basically, if you check the helium nucleus, you will see that helium nucleus contains only 2 units of positive charge. But basically 4 units of positive charge were combining to form only 2 units of positive charge. That means there is something. That means there is violation of charge, violation of energy conservation, violation of lepton number, violation of conservation of energy. Everything is violated. That cannot happen. So again, this problem came. So what is happening? Something is wrong. Is the equation wrong? Has Hans Bethe done everything wrong? But Hans Bethe was a master in nuclear physics. But we know very well that anyone who has read about this basic model of Bohr's model in even school level physics, the number of protons inside a nucleus should be equal to the number of electrons. The negatively charged number of electrons orbiting the nucleus will be equal to the number of positively charged protons inside the nucleus. In that case only the atom will become actually neutral. During the same time, around 1930s, there was another problem in nuclear physics which was coming out. Getting or discovering isotopes of elements. Same element having different shapes and different formats, basically, different, which we call as different isotopes, having some different kind of mass number, but the number of protons. So basically, there was an idea that whether is it possible that some kind of unknown element or some kind of unknown particle is actually present inside the nucleus, which has not been discovered yet. Ultimately, 1932 was a monumental year. This was the same year when multi-wavelength astronomy was discovered. Well, that is a separate story. What happened in particle physics was this. Two people called Curie and Joliot, they observed that when we are bombarding or when we are actually firing alpha particles, basically alpha particle means helium nucleus. When we are firing helium nucleus incident on beryllium, that is producing an intense gamma ray of having a huge energy of the magnitude of around 55 mega electron volt. Two of the masters during that time, Lord Rutherford, everybody, all of you have heard his name about particle physics. He's one of the greatest physicists. And one of his student, one of his research assistant, James Chadwick, who was a young physicist during that time, immediately they understood that this observation is wrong. And they actually established what is happening. They established the equation that what is happening is this. When alpha particles or helium nuclei is incident on beryllium, it actually produces carbon and another particle, not gamma ray, of this much abnormal amount of magnitude of energy. That is not the case. It produces a neutron. So this was the first time the discovery of the third particle, elementary particle took place. James Chadwick in 1932 is credited to have discovered this particular neutron by understanding the observations what was made by Joliot and Curie. And you all know, means if you read the history, you will see Chadwick actually received the Nobel Prize for discovering this neutron in 1935. So that was great. So what actually happened was this. Okay, that means by observing physics, by observing particle physics, another new particle came into being, and that was neutron. And as neutron was discovered, another problem started. You see, anyone who is doing science research or any research will understand this. If you do work, there will be problems. You cannot avoid problems. So what was the problem was this, basically this. The problem was, is it showing like this? Yeah, so problem was this. Problem was, again, going back to some history, that same violation of energy conservation and violation of conservation of energy was happening in this way. In 1896, the phenomena of radioactivity was discovered, and that phenomena was basically during those days known as beta decay. So it was discovered by in 1896 by Becquerel. Well, just 1 minute, let me stop the sharing and let me stop my video so that the internet will work fine, and again share my screen. Let me share my screen again. Now it will be fine. It can have some kind of problem with the internet. Well, so what was the story is like this. So during those days, it was not, that phenomena was not termed as radioactivity, it was termed as beta decay. Not going to details, the problem was this. Basically, if beta decay is happening, if you go to radioactivity, we'll see that radioactivity actually comes with a very basic understanding that if you just look at how radioactivity is happening, you will feel that conservation of energy is not taking place. So naturally, to actually preserve energy, people were actually telling, there were even eminent scientists or physicists like Niels Bohr, they were ready to entertain this idea in case of this radioactivity or beta decay, actually energy conservation is not holding. But one young scientist of that time, another great name, Wolfgang Pauli, he actually was adamant. He told in 1930 that no, energy conservation is happening, we are wrong. You people are thinking something wrong. There should exist another new particle which nobody has seen till yet. And it is almost very difficult to detect such a new particle because it is electrically neutral and it is almost having zero mass. It is very difficult to detect such kind of particle. It does not interact with matter. Almost it cannot interact with matter because that the mass is almost zero. And as a result, it will be very hard to detect. And that is why till 1930, nobody has detected it. So that kind of particle is also produced in radioactivity. And if we consider that kind of particle, then conservation of energy holds true. Nowadays, that particle is known as neutrino. And we have seen that it is actually true. The mass of neutrinos are very, very less, almost zero. As a result, it does not interact with matter. It can pass, if a neutrino is generated in sun, it can pass through the whole solar system without interacting with a single matter. It will pass through your body, it will pass through every matter, it will pass through the whole earth. And the amazing fact is, each and every second, innumerable amount of neutrinos are passing through the body of each human being without we being understanding it, because that is not interacting with any part of our body. How many of you know that each and every second, more than 10 to the power 30 neutrinos are passing through each of your body? Means one followed by 30 zeros. That many neutrino particles are passing through your body each second. Those all neutrinos are generated by sun. And you cannot feel it. They are all passing each and every second. You cannot feel it because they don't interact with matter. So naturally, it is hard to detect them. So what actually this person, Wolfgang Pauli, proposed was actually taken in a positive sense by another great physicist within 1 year. That was Italian physicist Enrico Fermi. Within a year, he actually introduced, he actually hypothesized, postulated that a new type of force should exist so that neutrinos can form. And that new type of force, nowadays we know it is known as weak nuclear force. That was the fourth type of force which was identified. It was one of the greatest intellectual discovery made by humanity, because identifying a fourth or a new type of force in 1933 by Fermi. What he told was this, what happens is this, the radioactive process goes on like this. A neutron can decay into a proton and one electron will be produced and one neutrino. Also, similarly, a proton can decay into a neutron and a positive electron, positively charged electron known as a positron will be produced and another neutrino. So basically, it was Enrico Fermi who actually termed these two particles as neutrino, the elusive particle which Pauli has introduced, which Pauli proposed. Here you see, before going to the story again, that there is something which is written here and here and here. Basically, Pauli would have been amused if he would have seen that not only a single particle which he proposed exists like the form of neutrino, neutrinos can be of 6 types. Pauli proposed neutrino exists, means one single new particle, and ultimately he would have been amused to see that 6 types of neutrinos exist. Each neutrino is having their particular family term name, means basically an electron can have an electron neutrino, neon can have a neon neutrino, tau particle can have a tau neutrino. And naturally, as electron has a opposite charged or antiparticle, opposite charged particle, which is positron, each of these 3 neutrinos can have their antiparticle. Means an electron neutrino will have an anti-electron neutrino, and similarly an anti-neon neutrino, anti-tau neutrino. Not going to the details of this particle physics, I will just come to this point that when we denote a neutrino, we denote like this. This E actually means this is an electron neutrino. And the bar above this neutrino sign means this is an anti-neutrino. Means this is an anti-electron neutrino. So this is why these symbols actually, this is what the symbols actually tell us. Now let us come to the point. Again, come back to the same reaction. In low mass stars, proton-proton chain reaction is happening and producing energy. We have actually encountered that 2 protons cannot fuse. In classical physics, the problem was already solved by a bold experiment and numerical calculations of George Gamow, who actually identified or who actually told that quantum tunneling is the only possibility by which protons can fuse, when protons can actually act as waves. And basically that is what is happening here. A proton is decaying into neutrino, one neutron, and then one positron is created and one neutrino is created. It is an electron neutrino. But if you look carefully, you will understand there is again a problem. So anyone having understanding about particle physics will tell me, what, you are talking something rubbish again. This cannot happen. A proton is lighter in weight than a neutron. Neutron is heavier than a proton. Then how can a proton, a free proton, how can it decay into a neutron? Well, somebody can tell me, well, Fermi said or this, so it is happening. But mind it, my friends, Fermi told very carefully, scientists are very clever, you know. Fermi told very carefully that a proton can decay into a neutron inside the nucleus, where there are some other protons nearby. So if there are protons nearby, then one proton can borrow some energy, some momentum from the another proton, and it can decay into a neutron. But a free proton can never decay into a neutron. How can it decay? Because it is lighter than a neutron. So basically, in that case, another, apart from this impossibility, if someone who is extremely good in particle physics, he will also tell me or ask me, there is another problem, sir. The problem lies in this equation. This equation is actually almost impossible inside Sun. Why? Because this is a very slow equation. The time scale required for 2 protons to come together, ultimately fuse together through quantum tunneling effect and producing this heavy hydrogen, the time scale required for such coincidence to happen is huge. Actually, through rigorous calculation, it has been shown that in solar interior, it can take 10 to the power 11 years for 2 protons to come together and fuse together. So how Sun is actually shining? If only 2 protons fusing together can take 10 to the power 11 years, then how energy is being produced inside Sun? Well, the answer is this. Because inside Sun, there are extremely huge number of protons. See, Sun actually contains, a Sun-like star, at least 10 to the power 57 protons are present. So now the probability of protons, many protons coming together and fusing becomes yes. Although the time scale for this reaction is very slow, for 2 protons to fuse, as so many protons are available, then 2 protons coming together and fusing, and ultimately proton decaying to a neutron, that all these possibilities are true because sun actually contains so many protons, 10 to the power 57 protons. Again, the same question is there. You can ask me where is the proof? Again, you are telling the same thing. It is happening, but it should happen. If it is not happening, then we should not see stars. So now the question comes, where is the proof? All you are telling is about it is happening, otherwise if this does not happen, then stars will not be there. But you are just telling like something like it's telling like a conclusion. It is happening. So now let us come to that great part of this story. The end part of this story was people were like you people were actually becoming frustrated. The scientists were becoming frustrated. Okay, we have to have some definite observational proof. But the problem is this, we cannot see the stellar interior. It is invisible. But we whatever happens, we have to see that this nuclear fusion is actually happening, and then only we can tell all these extremely unbelievable talks or unbelievable statements which has been present are actually true. So scientists started looking, okay, we cannot see the stellar interior, correct. But we, according to our numerical calculations, we know what kind of reaction is happening inside the star. So can we detect any particular element or any particular particle which is directly coming from the interior, stellar interior? Can we detect that? The energy which is generating, high energy radiation which is generating from the interior, that will take millions of years. Sun also, it takes around 30,000 years to reach the surface. Within that time, that radiation will actually decrease in strength, energy will decrease, and the radiation which is originated from the photosphere of sun will tell you about the details of the photosphere, not the stellar interior. Well, then you cannot take the energy you cannot get from interior. What about those positrons? See these positrons which were being produced. So now these positrons are very unstable. They will immediately after production in the interior only, they will interact with one electron and they will annihilate. So positrons also you cannot detect. So what is left with us is actually these neutrinos. Basically, we have already told, it is already proposed that neutrinos are the particles which do not interact with any matter, and as a result, they will actually pass after originating from the stellar interior. They will directly pass through the stellar interior and they will come to Earth. And these neutrinos are like the witnesses of a crime. The actual place where energy generation is taking place, if that is a crime scene, so these neutrinos are the only particles which witnessed the crime happening. So if we can actually detect neutrinos coming from sun or stars, then we can say that, okay, whatever we have told for 50 years of study, particle physics study, is correct. But basically, I have also told you the dilemma is here. Neutrinos will come to us because they don't interact with matter. So how can we actually think of detecting neutrinos? We will also not be able to detect neutrinos. Basically, these neutrinos are extremely elusive. They are like ghost particles. They are like ghosts. So basically, they are hostile witnesses. So they have seen what has happened in the crime scene directly, and they are not willing to tell that. They will just pass through the earth within seconds, and you will not be able to capture a single neutrino because they don't interact with matter. But what to do? Scientists understood that the only way by which we can actually tell that energy generation is actually happening in the stars as we have proposed, the only way to tell that our theory is correct is actually detecting neutrinos coming from the interior of stars. There is no other way. But how to do that? And that started one of the most impossible feat in the history of humanity. This story has become a detective story and one of the greatest triumphs of humanity from that day onwards, from 1964 onwards. In 1964, one master nuclear physicist, John Davis Jr., actually Raymond Davis Jr., and one of his student, John Haeckel. They actually started one very good experiment, one of the finest experiment ever done in the history of physics or in the history of science. Say 1964, what they thought of was a grand experiment. What we can do is this basically. So make one huge tank, and this tank will consist of some liquid. This is a cleaning liquid which you see, which you can find in your drying machines and all these things, C2Cl4. So this will be what they thought was there will be a steel tank, and they made it. There will be a steel tank containing 4 lakh liters of this particular cleaning liquid. And this detector, this tank will act like a detector. This was placed 1 kilometer underground. It was placed in a gold mine in USA, Homestake Gold Mine. What was the idea? Idea was this. When a neutrino, which is being produced in the sun's interior, mind it, inside sun, electron neutrinos are produced. So when neutrinos will be produced, they will automatically come and pass through the earth. So basically what will happen, inside this tank, when these neutrinos will be passing, they will act with this chlorine, and ultimately some argon will be produced. The goal, the target was to detect how many number of argon atoms are being produced inside the tank. And there was a threshold. Basically, this means any electron neutrino having energy less than 0.8 mega electron volt will not be
Gaurav,
detected.
sorry to interrupt, Gaurav.
Yeah.
Try to wrap up in a few minutes.
Okay.
So after that,
Fine.
we will take questions.
So let me wrap up in 5 minutes.
Oh,
So basically, this was the idea that we should actually, the neutrinos will come, it will interact in that tank with chlorine, and it will ultimately generate argon. The target was to count how many argon atoms are produced in the tank, but it was not easy. The target was almost an impossible target. The tank was containing 10 to the power 30 atoms, and how many argon atoms will be produced per second? Only 15. So this was the target which was being achieved actually by these two people. This is the picture of the real tank. You see John Davis, Dr. Davis, Raymond Davis standing here. And this is a funny picture. Sometimes they will actually go inside that tank. They will just take a bath in that cleaning fluid. So that was also Davis. So basically what was the result was this. They did run this experiment with proper understanding, with detailed computer modeling for 4 years. And after 4 years, they found something great. They indeed detected solar neutrinos coming, but there was a something was missing. The amount of solar neutrinos which was predicted, which should come, they detected 1/3 of that. Means the number of argon atoms which should be created, they detected 1/3 of that predicted atoms. Naturally, people can say, okay, this can happen. There are so many errors. So only 15 atoms detecting out of such a huge tank, there can be errors. Nothing to worry about this error factor of 3. You can take it, you can consider it. But astronomers are not like that. There are well-known, there are obviously any good astronomer will never sit quiet if they understand that their understanding of astronomy is correct. Naturally, this result tells about 3 possibilities. So, well, neutrinos, the solar neutrinos, how it is detected in the standard model of sun. I'm not going to any details of units and all these things. The possibilities can be 3. One is the theoretical calculation is wrong, means the standard model of sun which we are calculating is wrong. Another possibility can be the whole experiment is wrong. And another drastic possibility can be, if both these are correct, then whether there is something wrong in fundamental particle physics. And that gradually hit the brain of astronomers also, theoretical physicists also, particle physics. No group was ready to accept their defeat. So astronomers were telling our standard model of sun is 99.9% correct. Particle physicists were telling our particle physics is 100% correct. Experimentalists like Davis and vehicle, they started doing the same experiment repeatedly. They did intense research. They developed modern techniques to do the experiment, and they came out with the solution. Our experiment is also correct. Now, basically, I will not go to the standard model of sun and all these things. So what is the possibility? The only possibility which lies is, if everything is correct, as Sherlock Holmes told, if every possibility, if you rule out Dr. Watson, then the most unbelievable possibility which remains is should be true. So basically, Bruno Pontecorvo and Vladimir Gribov, two Russian physicists in 1969, they came up with actually one particular drastic suggestion. They told that the third possibility is actually the case. Something is dramatically wrong in the understanding of particle physics till 1969. And it was actually true. What they told was, think like this. What if neutrinos can actually change their identity? Neutrinos oscillate in flavor. What if the electron neutrinos which are being generated from the sun while traveling to Earth, they are actually changing their identity to muon neutrinos and tau neutrinos. So if neutrinos can change their identity, just like you see this Dr. Jekyll and Mr. Hyde. So somebody doing a crime, and while traveling to the police station, that person is changing his identity. And as a result, same thing if neutrinos can do, some neutrinos will be electron neutrinos when we are tracking from Earth, and other neutrinos which we cannot track will be naturally tau neutrinos and muon neutrinos. See, if three types of neutrinos can actually change their identities, then only 1/3 of the neutrinos will be detected in that chlorine experiment, because the chlorine experiment can only detect electron neutrinos, not the other two types. People did not believe it. Whatever you are telling is something extremely drastic. You are telling that fundamental particle physics is wrong. So great physicists have worked for 100 years in particle physics. And ultimately, you are telling that particle physics has something drastically wrong. People did not believe. So what happened? Some more experiments came up into time. In Japan, there was an experiment of Kamukande. Same kind of experiment was done. But here, liquid water was used in the form of detector. A tank, which is heavy, huge, 16 to 16 meter tank. It contains 3,000 metric tons of water, and there will be inside the tank there will be 1,000 photomultiplier tubes. Why? The reaction which will happen is this: a neutrino, when it comes, hits an electron inside the tank. That electron will be scattered, and in the meantime, there will be a radiation which will be produced, which is known as Sherenkov radiation, and that radiation will actually produce a bluish kind of light. The photomultiplier tubes will be able to detect that light, and as a result, it will be able to track from where the neutrino has come. It was a kind of neutrino electron scattering experiment. So this Kamukande experiment had some disadvantages. Basically, it can actually detect, it was able to detect all flavors of neutrinos. And as a result, when the results came, they also observed a discrepancy, but they actually detected 45% of the neutrinos of what has been predicted. Naturally, people from that day onwards, 1989 onwards, started, even the greatest physicists started doubting that yes, something is very, very wrong, might be very, very wrong in particle physics. And what drastic suggestion this Pontecorvo and Vladimir has given might be correct. Neutrinos actually oscillate in flavor. So what we can do is, this was another kind of experiment we can do is make the experiment bigger. Can we make a bigger experiment? The Kamukande experiment was replaced by Super Kamukande, similar kind of experiment where everything was much, much bigger. It was again in Japan. This time it was 32,000 tons of pure water in the inner volume, which was covered by an outer volume of 18,000 tons. And instead of 1,000 multiplier tubes, there were 11,000 photomultiplier tubes. Same thing, electron scattering will happen and Sherenkov radiation will be produced. And result was again the same. It did also, as it can detect three types of neutrinos, it detected 45% of the neutrinos. And this is how actually the tank looked like. Basically, to check the photomultiplier tubes, there were boats with which engineers and scientists used to go inside the tank. So this is something of very fantastic picture, not going to details. There are some other experiments which were carried out in Italy and Russia, where these are known as gallium experiments. They were also sensitive to only electron neutrinos. So as a result, basically the result also hinted that the experiments which can only track only electron neutrinos, they are detecting 33% of the total predicted flux. And basically the mystery deepened, and this belief started crumping that yes, something is wrong, something we should correct in understanding of particle physics, fundamental physics. And most probably, we should make one particular experiment which should settle everything. And that experiment was ultimately the Sudbury Neutrino Observatory in Canada. It is a huge experiment. It was containing heavy water, not normal water. It was containing deuterium water. Like the same way, there was an inner volume, there was an outer volume, inner volume containing heavy water, outer volume again containing huge amount of water. And after that, this whole assembly was ultimately fixed in a rock cut, because it was 2 kilometers underground in a rock cut assembly in a steel trunk type of system. This was the actual case. It was suspended. It was huge. And this was the experiment where it was designed in a way that this experiment will run in 3 channels. First will be this kind of channel where neutrino absorption will be taken place, and it will produce that same kind of Sherenkov light, which can be detected by photomultiplier tubes. Remember, this first channel, this first channel experiment is only sensitive to electron neutrinos. The second channel, where same electron scattering will happen, that was sensitive to all flavors of neutrinos. And the third channel, where neutrino will be absorbed, that was also sensitive to all 3 flavors of neutrinos. Now see what the result came. In the first run, the first channel was given the chance. Naturally, the first channel was only sensitive to electron neutrinos. As a result, only 35% of the predicted flux was identified. People understood that now we should run all the 3 channel experiments at the same time. And on 18th June 2001, a historic announcement was made. That was one of the greatest triumphs in the history of science, in the history of humanity. What happened was, after running the experiment in all 3 channels, converting them to numerical values, it was found that in channel 1, which is sensitive to only electron neutrino, we are able to detect 35% of the total flux, whatever is predicted. But in channel 3, you see, whatever has been predicted, as channel 3 was sensitive to all 3 flavors of neutrinos, we were able to detect 100% of the solar neutrinos, which should come from sun per second per square centimeter. So this was one of the greatest achievements, one of the greatest results which we achieved through any experiment in the history of science. And so elated the science community, physics community, astronomy community was, that I will again go back to this last slide, which tells the same story. Go back to that 18th century philosophers who told that it is not possible to study stars to understand stars. Come back 100 years later, in 1924, Eddington told that, is there any tool through which we can pierce the outer layers and see what conditions are actually happening, what conditions are actually occurring inside a star's interior? And in 2001, 18 June, after this Sudbury Neutrino Observatory experiment, John Behkel actually commented this famous statement, the smoking gun has been found. And after that, doing their experiment, they ultimately understood, they ultimately found that yes, neutrinos actually oscillate in flavor. Neutrinos do change their identity in flavor, and if we can set up our experiment which can detect all 3 flavors of neutrinos, then exactly the exact amount of neutrinos which our calculations tell us should come from the solar interior, exactly that amount of neutrinos are coming from solar interior. And that has been detected with 100% accuracy. We really found actually the tool which can look inside the stars. That is why it is considered as one of the major success in the history of mankind, and obviously in the history of humanity, in the history of science, and obviously in the history of physics, because it showed that how physics can actually mix and how different branches of physics can help each other. Today is the time when everything is much more improved. And as Archana madam has already told, that it is a time when we should look beyond. Let me thank everyone looking at this beautiful picture of the huge galaxy, huge universe containing innumerable number of galaxies. And ultimately, it is our human intellect which ultimately possesses the best machine in the universe, not the universe. And that machine is actually our neurons, the nerves, the intelligence. Let me thank all of you. Well, thanks to everyone for listening to this. And
Thank you, Gaurav.
now
This
we can
is
go for the
wonderful.
questions.
Yeah, let's do a virtual applaud for Gaurav. It was, of course, the most incredible story that we are still trying to come to grips with. There are so many open questions, but let us first look at questions that have come on the chat. First question is from Shraddha. And the question is, of course, very related to fusion, China's artificial sun. As you know, that for 101 seconds, China was successful in creating millions and millions of degrees inside its tokamak. So how does that present itself to the world? That's her question. And how could possibly it have an effect on the energy problem of our planet? Gaurav, your thoughts?
Yeah, it's a nice question, Shraddha. Yeah, see, as we know that for more than 100 seconds, China was able to lit this artificial sun. So if actually in future we will be able to do this, I believe that we will be able to do this. It can actually help in solving, at least may not be the full, but at least a part of this energy problem which we are facing nowadays, almost in various parts of the world. It can be. So I look into this question with some positive note. The future should be positive. Yes,
Thank you, Gaurav.
problems will be there, definitely.
Of course.
But we should be positive.
Yes, I mean, we have to, of course, it is a far way off where we are going. It will take, I don't know, 20 years, 30, 40, 50 years, up to the point where we can actually think of using that as energy source for the planet. How are we creating the tokamak? Is it green? Is it, clean? So there are many, many questions. And Shraddha, it's a great question. Like Gaurav said, please look more into this. There is also the ITER project in France doing similar activity on fusion. And India is a very big partner also in this project. So please do engage, and there are many, many opportunities to learn and engage in this project. Next comment is coming from Naman. Thank you, Naman, for your comment. How developments at CERN on very small particles. Yes, indeed, this is very fascinating. There's a lot of work on neutrino physics that goes on at CERN, especially experimental neutrino physics, because there is something called the CERN neutrino platform, which is building a module for the Dune experiment, again, for the United States. So there are many, many studies that are going on to understand neutrinos, neutrino oscillation. There is also the Gran Sasso laboratory in Italy, where a neutrino beam is beamed from CERN to Gran Sasso, 700 kilometers away. And of course, neutrino oscillations are studied in great detail. So indeed, it's very fascinating, and many, many opportunities here as well. So let's look further. INO. Now, Gaurav, you want to speak something about INO? I do not want to say. Apart from
This is a fantastic project. Actually, I had the opportunity to meet these people, Navakumar Mandal, once in a conference in Guwahati, actually. So, and that was also the same conference where we met these three musketeers together, Arindam and Pallab and me. So we became friends. Yeah. So basically, India Neutrino Observatory, which should come in future, there are some problems going on because some problems related to land and all these aspects, but that might be sorted out in future. It is true that it is taking around more than 20 years have been over. But yes, of course, we need a neutrino observatory in our own country. Actually, there are very few people who might know that the first detection of atmospheric neutrinos happened in TIFR Mumbai. And it was done inside Kolar gold mine near Bangalore. That was the first detection, successful detection in 1964 of atmospheric neutrinos. And that was also the experiment which gave this hint, proper hint, that neutrinos can oscillate. So basically, we need such an INO, and it should come. And neutrino research, neutrino astrophysics research, neutrino research will definitely progress if such an observatory is coming forward.
Yes. So here we need the three musketeers to actually work more on outreach, because for INO, where we have failed in India is outreach. The political problem has occurred because people have played on the fact that this is somehow radiation, and they have been saying that neutrinos will pass through my body. And they do not realize that how many millions of neutrinos they pass through their bodies all the time, like you mentioned, Gaurav. But people think that, oh, radiation, something will happen to me or my crop or to my cattle or to my elephants, So we have to be very careful, and we have to do a lot of outreach in educating the general public about why INO is needed in our country, I think. So that's really one agenda that we do need to take on further. Okay, other questions? Otherwise, I also have a couple of questions. But we have 2 minutes.
I'm having some question.
Yes, Arindam.
Yes. Before I just ask my question, I must appreciate and admit that, Gaurav, your talk is always a pleasure to listen. Okay, it's a fantastic journey rather than a presentation. It's a journey. Okay, where we learn something in a fascinating storytelling way. Okay, thank you very much for this and a complete amalgamation, excellent amalgamation of what we learned: nuclear physics, particle physics, and also the astrophysics. Anyway, so my question is regarding that CNO chain reaction and that proton-proton reaction. That how it was actually known that for objects to greater than 2.5 times the solar mass, that CNO reaction is taking place, and in case it is less than 2.5, the proton-proton reaction is taking place.
It's a beautiful question. Basically, apart from so as it is a huge story, there were some things which I was not able to tell, but basically it was due to another Indian astrophysicist known as Chandrasekhar. Yes. Subramaniam Chandrasekhar, who was a young genius. He was obviously a genius. He was very young during those times, but within an age of 25, he actually, apart from giving something known as Chandrasekhar limit, he was actually also the man who gave maturity to stellar astrophysics. He solved almost all the major problems of stellar astrophysics, which was remaining in 1930s. So one problem which he solved, one proposal which he actually proposed by mathematical calculations is, see, in case of low mass stars, convection and radiation both plays role. But as the mass of a star increases, he showed that radiation starts dominating rather than convection in the interiors, basically. So if the mass of a star crosses a certain limit, maybe it is 3 or 3.5 times that of Sun, then he showed that in a massive star like that, radiation will be contributing the maximum amount of outward pressure which is being generated inside the core of the star. So that numbers, I am not going, without going to the numbers, what I am trying to say is this, that taking Chandrasekhar's understanding, it was understood that as mass increases in the interior of the stars, the temperature will also increase, provided the stellar interior is acting like ideal gas. And it acts like that in a normal situation. So in ideal gas situation, what happens? If temperature increases, naturally energy rate will increase for energy production rate. And this energy production rate is very less dependent to temperature in case of low mass stars. So in that low mass star situation, the energy cannot be produced with some reaction system which is highly dependent on temperature, and that is the Cno cycle. So Cno cycle is extremely dependent on temperature. If you just increase temperature by some fraction of Kelvin, the energy production rate will increase drastically, exponential. That can only happen inside high mass. That kind of temperature should be present so that carbon will be present. So as a
Gaurav,
result,
this is
Uh,
really
in
fantastic. If
in
I
that
can say
case,
that. Yes.
Gaurav, just want to interrupt you one thing. In case of high mass stars or higher mass stars, gravitational collapse will also take place in such cases.
yeah, but there is outward pressure.
Yes.
Energy generation is high, outward pressure is balancing in a case of
Right.
normal high mass star.
Okay.
Fantastic.
So
I think, Gaurav, this has been an amazing session. Also for me, learning session as well, because there are so many new things I have learned, and you explained very well in this storytelling way. That's fantastic. So I can propose something, Gaurav, because there are many, many questions, and we all feel that we are still hungry to learn more. How about that we, at the end of the month, Pallab, you create a Q&A session with the experts, after we finish the other speakers, let's have a dedicated Q&A session with each speaker, getting the questions perhaps in advance. That will really help. And then they can sort of really shed light on the questions. And this is so wonderful to listen. But unfortunately, the time is now really the constraint. It's 1.5 hours, and I have another meeting also I would like to now switch to. So I think there's no other question, but I must admit that with all of you, we have to thank Gaurav for this wonderful, wonderful talk.
Absolutely.
And you have to do it once again, because this was somehow not as well attended as I wanted it to be. And Pallab, we have to work harder next time so that, we can have more engagement and we can have the poster announced at least 1 week in advance or 2 weeks in advance, something like that.
Ma'am, actually, we need, more outreach of our outreach program.
JJ, that's what I need your help for. And we have to look
Absolutely.
I am looking at you all with 100 teachers behind you, and that is the multiplier effect we are looking at, So,
Vishaka is also here. Vishaka
yes,
is also
and exactly. So this is the core team that is here, and we really are depending on all of you. And Vishaka has actually created an SOP which we are going to use from next time. Vishaka, you take charge and tell everybody what they have to do. Okay? You are muted. One more minute and we will close. Yeah.
Yes, ma'am. For sure. I think, I'll be able to help a lot in this. In the outreach also, how it has to be done. So for that, I'll request all of you, whosoever is the part of the group, all the members of the group, that we have to meet very regularly to discuss each and every aspect of the programs, and us also, that how we are taking it forward. So let's just, go ahead with weekly meetings. And in case if there is an event, there has to be more energy that needs to be channelized here. So I will take you all through that later.
Yeah. Can you, Vishaka, just start scheduling this and then create like a weekly slot, which is convenient for everyone. We will come on board and we will, attend. Whoever can attend. Let's not sort of force, because this is all a voluntary exercise, So whoever can come, they should come. And if they take a responsibility, then they have to deliver. That's the kind of way we have been working to now.
Sure, ma'am.
So next session, Pallab, you, Vishaka,